Circuits. An electric circuit is a set of electrical components that provides one or more complete paths for the movement of charges. Let's take a look at all of the parts that could make up a circuit. Examples include a resistor, an open switch, a closed switch, a battery, a light bulb, and a voltmeter and ammeter. These are all symbols representing each of these objects because drawing each of these objects in real life is quite challenging. So physicists have decided to use these symbols instead. A resistor is represented by this squiggly shape. A switch that is open has a broken circuit. When you close the switch, you can see it completes the circuit. This symbol right here represents a battery. You might not think that it looks like a battery, but actually if you imagine it like this, where like this long part right here is like the fat part of the battery, and this short part right here is like the little nub, it actually resembles a battery pretty well. This symbol shows two batteries touching. Down here, this is a light bulb. I suck at drawing light bulbs, so I do it like this, just like a line with a little swoop and then draw a circle around it. That's what my light bulb looks like. And lastly, a voltmeter and ammeter. Those are devices that are used to measure voltage and current. When you put all of these together, you can create a circuit. You can see that circuit drawings in physics are drawn with the wires in straight lines and right angles, that all the objects are put together to form like this square shape. And that's just for ease of reading. Let's compare the two primary types of circuits, series and parallel. A series circuit looks like this. This is what it might look like in real life. This is what its schematic drawing looks like. And then this is a parallel circuit. This is what this might look like in real life and its schematic drawing. You can see that in a series circuit, the resistors are all in a line and that the electrons have one path to follow. The electrons that leave, you can imagine them leaving like in a single file line, and that each of these light bulbs that they hit is like a stop that they have to make. I like to imagine electrons as like people in line at the grocery store. And this is kind of like Costco, where at Costco you have to stop at one register and check out. And then you have to stop at like this other station on your way out the door where they like check your receipt. You have to make two stops. So in a series circuit, the electrons leaving the battery will like stop at this resistor and then continue on their way and then stop at this resistor. And since they're all following down one path, they're all moving all at the same rate. To find the total resistance of the circuit, you just add together the value of these two resistors. In a parallel circuit, you actually have a branch. You can see that if you were an electron leaving this battery, that you'd hit this spot and you'd have a choice. You have multiple paths to follow. I like to imagine this kind of being like at a grocery store when you have multiple checkout lanes open. You approach the checkout lanes and then you can choose to go this way or you can choose to go this way. The resistance equation is made up of these inverses, and this implies that as you add more and more resistors, that you're giving the people at the store more and more options to check out, reducing the total resistance of their circuit. So how does that affect their current and voltage? In a series circuit, the current is constant throughout the loop. That makes sense because as an electron moves through the path, all the electrons are moving at the same rate in a single file line. When they reach this spot, they all have to stop. And when they reach this spot, they all have to stop. And so you can imagine them all like marching along one behind each other, and they're all moving at the same rate around the circuit. So however fast one of them moves, the speed that all of them have to move. But its voltage is split along the loop. Energy is lost in each resistor. You might remember that voltage you can kind of imagine as being your desire to continue. And that voltage is equal to like a change in potential energy per charge. So what happens is that you can imagine even just like falling downhill. That's a change in energy. So let's say like a charge is like at the top of the hill, and then it has like potential energy. It turns into kinetic energy at the bottom of the hill from potential to kinetic. So here you have lots of PE, and here you have no PE. The same is true in a circuit. So if you have, for example, a lot of voltage on this side, let's say this is like a 12-volt battery, that means on the opposite side, you would have 0 volts, and that the electrons, you can imagine, are kind of like falling downhill. And their energy is going to be lost in each resistor. So like on this, like if the electrons are like traveling this way, let's say they're like boop, 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 I'm an electron, boop, 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 boop. Over here at this side, they would have 12 volts. And when they go all the way through it, they'll have 6 volts. They'll have lost a total change of 6 volts in this bulb. And then when they make it this way, boop, 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 they'll start with 6 volts and they'll end with 0 volts. They'll lose a total of 6 volts in this bulb. So you can see that energy is lost at each resistor and that the total voltage is split along the loop. Each one of them would have an equal amount of voltage. If they were equal resistances anyway. So if you added like a third light bulb right here, and this was still a 12-volt battery, then you might have 4, 4, and 4 volts along each. This one going from 12 to 8, this one going from 8 to 4, and this one going from 4 to 0 volts, and ending up at 0 volts at the end. Parallel circuits are completely different. Let's take a look at a parallel circuit. In a parallel circuit, the current is going to split among the loop. Each loop is going to add to the total current. So let's say that electricity is leaving. Boop, 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 boop. Let's say that there's like 10 electricities. Whereas over here in the series circuit, if there was 10 currents of electricity, it would be 10 currents throughout the entire loop because it's a single file line. But over here in the parallel circuit, if there's 10 currents, it has the opportunity to split. If these are equal, it might be 5 currents and 5 currents in each branch. Or let's say if this light bulb has more resistance, then the electrons might travel in the path of least resistance, and more of them would travel this way and less would travel this way. So maybe you'd get like 7 and 3 or 8 and 2, and they'll add up to the total current, but the current splits among the loops, and the current before would split into the 2 branches and equal the current after. But the voltage is constant, and that's because each of these is connected directly to the battery. Whereas over here in the series circuit, the electrons had to travel through each one of these in turn. Over here, the electrons only have to go through one light bulb. So when you are examining its voltage, if this battery right over here is 12 volts, as the electrons travel, boop, 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 it's going straight from 12 to 0. So each one of these light bulbs gets the full 12 volts because the electrons just have to travel inwards and then exit. They only have to take one path. So the voltage is going to be constant in each loop in a parallel circuit. Let's do some examples. Here's an example series circuit. You can see that this is the total voltage, current, and resistance, represented here by the 12 volts of the battery, and that each one of these are labeled resistor 1, resistor 2, and resistor 3 right here. We're going to start off by calculating the total resistance. In a series circuit, you would just add them together. So 1 plus 2 plus 3 would give us a total resistance of 6. To find our total current, we would have to use V equals IR. If our total voltage is 12 and our total resistance is 6, that gives us a current of 2. Since this is a series circuit, that means that if you have 2 currents leaving the battery, that at this point you would have 2 currents. And as you continue onwards, at this point you would have 2 currents, and at this point you would also have 2 currents. Once we've determined that, we can use V equals IR for each of these to calculate the voltage on each resistor. So 2 times 1 is 2. 2 times 2 is 4. And 2 times 3 is 6. So these are each of the voltages, remembering that the voltage is their desire to continue, and that the total voltage here has to equal the total of the circuit. So 2 plus 4 plus 6 equals 12. That's a way of checking to see if we did it right. You can see that the current does not add up to equal the total current, and that's because the current that we start out with stays constant. But the voltage we start off with does not change or stay constant. It changes throughout the circuit. Let's do our next example of a parallel circuit. All right, here's a parallel circuit. You can see that this is the total voltage, current, and resistance representing this 8-volt battery and each of these resistors. Resistor 1, resistor 2, and resistor 3. Our first step is to calculate the total resistance, which would give us 1/5 plus 1/7 plus 1/9. Let's find out what that is. That is 143 over 315, or 0.453. That's not the answer, though. Many people might think that's the answer. This is not the answer. This is 1 over the answer, right? So in order to find the answer, we have to take the inverse of that. So the resistance will be 315 over 143, which is equal to 1 over 0.45, or approximately 2.2. Knowing that, we can, in this column, calculate V equals IR and use the voltage and the resistance to calculate the current. I got 3.63. Now, since this is a parallel circuit, each one of these is going to split that current. If these were equal resistors, then each of these would get 1/3 of the current, but they're not. So we now have to take into account the fact that each one of these has 8 volts of electricity traveling through them, because each of them is connected directly to the battery. And then we can use V equals IR to calculate the current in each resistor. This one will be 8/5, this one 8/7, and this one 8/9. I'll find that decimal equivalent. And we can check our work, because these added together should equal 3.63. Let's do one last example. The purpose of this is to show how current splits in a parallel circuit. This is a parallel circuit. It's drawn kind of weird. This is the equivalent circuit to something that looks like this, but this is hard to draw. So to make it like boxy, this right here is equivalent to this. This problem doesn't have a table attached, so I kind of have to create my own table. Let's look at the total voltage. We'll find the total resistance and use that to find the total current. So the total resistance, 1/3 plus 1/4 plus 1/6 gives me 3/4. So the resistance is 4/3. Which means our total current is 9. So you can imagine traveling out of this is 9 currents, all following in a line, boop, 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 boop. How many currents do we have at this spot? Well, that's going to be 9. Put 9 down here. Perfect. All right, so as that current continues on this journey, boop, 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 it has a choice. It can split and go this way, or it can split and go this way. So let's take a look at how much of these 9 amps is going along this path. This path has the full voltage of the battery. So if its voltage is 12, its resistance is 3, we can use Ohm's law, V equals IR, to find that its current must be 4. So that means that of these 9 amps, that 4 amps are going down this way, which means that 5 amps are going this way. So let's follow these 5 amps along their path. Boop, 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 boop. 5 amps, 5 amps. They reach this junction. Some of those 5 amps of current are going this way. Some of them are going that way. Let's calculate how much. Taking a look at this resistor is also directly connected to the battery because electricity can leave the battery and travel to this point without traveling through any other resistors. So if this one's voltage is 12 and its resistance is 4, that means its current has to be 3 amps, which means that of the 5 amps traveling this way, that this branch right here has 3 amps, which means that this branch right here has 2 amps. So following this 3 amps down, this is 3 amps. Following this guy down, this is 2 amps. All right, these 2 amps and these 3 amps are going to meet back up at this point. So at this point, this resistor right here is going to have 5 amps. And that 5 amps is going to continue and meet up with this 4 amps right here. So if we were to measure at this spot what the current is, it would be 9 again. Nice work, guys.